Assalamu alaikum and good morning, everyone. Sia, can you hear me? Assalamu alaikum and good morning, everyone. Today, our topic is thin film deposition, and the outline of this presentation is chemical vapor deposition, physical vapor deposition, evaporation, sputtering, and strengths and weaknesses of these techniques. This is a very good presentation, and I have taken it from one of the best universities of America. And with little bit of addition and subtraction, this presentation is, I think, quite reasonable to present. So we will begin from the first slide. The first slide, first of all, we have definition of chemical vapor deposition. What is chemical vapor deposition? It is a technique, it is a vacuum deposition method, not technique, but a method. It is a vacuum deposition method used to produce high quality, high performance solid materials. The process is often used in the semiconductor industry to produce thin films. And physical vapor deposition, PVD, because these both are the very important techniques used in the deposition of materials. So PVD describes a variety of vacuum deposition methods which can be used to produce thin films and coatings. PVD is characterized by a process in which the material goes from a condensed phase to a vapor phase and then back to a thin film condensed phase. So this is overall we call this process as physical vapor deposition. Evaporation is a type of vaporization that occurs on the surface of a liquid as it changes into the gas phase. So this is actually happening at the surface of the liquid. And sputtering is a phenomenon in which microscopic particles of a solid material are ejected from its surface after the material is itself bombarded by energetic particles of a plasma or gas. The issues related to thin film deposition are, first of all, the quality. In quality, composition, defect density, or pinholes, contamination, mechanical and electrical properties are affected by these. Quality of the thin film, good adhesion, minimum stress is required for high quality. Topography, uh, for topography, uniform thickness on non-planar surfaces, step coverage, conformal coverage, you should be uniform, space filling in holes, channels, voids, etc. These are the things that should be covered while depositing the thin films. Here you can see this is metal coating, this is outside coating, and here is the defect. This portion is a defect. This shows good metal filling of a wire or contact hole in a dielectric layer. And in case of B, you can see this one. This is the defect, silicon dielectric filling, the space between metal lines, the poor filling leading to void. So this is a void in the thin film coating. So this isn't required when you deposit the thin film. And similarly, we have defect over here. This portion is the defect. And over here, the deposition is not so uniform. In C, poor filling of the bottom of a via hole with barrier or metal. So these things are not required like this one. These are the voids in the deposition of thin film which are not required for high quality thin films. Two types of thin film deposition, CVD and PVD, chemical vapor deposition and physical vapor deposition. In CVD, chemical vapor deposition, reactive gases interact with substrate and used to deposit silicon and dielectrics. Number 3, good film quality. Number 4, good step coverage. CVD gives good step coverage as well. In case of PVD, number 1, used to deposit metals, and it deposits high purity metals. Line of straight or straight. This is how the deposition occurred during physical vapor deposition. In CVD, following are the steps that are following are the types that are used to deposit the thin films. You can see here in the diagrams and over here in the written form, gases react with substrate. This is the first step. Various types of CVD are atmospheric pressure, APCVD, low pressure, LPCVD, plasma enhanced, PECVD, high density plasma, HDPCVD. CVD systems, you can see here, this is a CVD system, and here the gas control and sequencer. Source gases are present over here. This is a vacuum pumping that pumps and creates a vacuum inside the tube. And here are the carrier gases that take part in the reaction in the tube. So in number 1, APCVD, or we call as cold valve for deposition of epitaxial silicon, used for this purpose. LPCVD, hot valve for deposition, polycrystalline and amorphous silicon. So these are the major uses of these techniques. The steps involved in CVD are the following 7 steps. First of all, there is a transport. There is a transport of reactants via forced convection to reaction region. And at number 2 and 3, transport reactants via diffusion to wafer surface. And number 3, adsorb reactants on surface. Number 4, surface processes, chemical decomposition, surface migration, site incorporation, etc. And number 5, desorption from the surface. And number 6 is transport byproducts through boundary layer. Transport byproducts away from deposition region is the last step. This is how the byproducts are transported away from the surface. So these are the 7 steps that are involved in a CVD process. This is auto-doping occurs. You can see the steps also. So this is very commonly used technique for the deposition of thin film CVD. Advantage of LPCVD, low pressure chemical vapor deposition, faster growth. It gives faster growth, less auto-doping. Little diluent gas needed, lower gas consumption, fewer byproducts or particles are involved in this LPCVD. Disadvantages are the high temperature required to carry out this deposition. Poorer step coverage because step coverage is not very good. Slow deposition rate. The deposition rate is very slow and it takes a lot of time for the deposition of thin film. plasma enhanced CVD, this is one of the, I mean, this technique is much better compared to the simple CVD. Good when temperature is restricted. It has, advantage of a simple CVD process. Provides reasonable deposition rates, good film quality, conformal, and but it may also leave unwanted byproducts on the film. So in this, you can see the plasma is generated over here, and then we have wafers, electrode, or heaters down here, gas outlet, and this is a gas inlet, silicon hydride, oxygen are going through into the chamber, and they are coming out. The gases are coming out from this outlet, and this portion is grounded electrically, and RF power input is provided from here. So these are the steps, and this is also the advantage and limitations for PVD. Versatile deposits almost any material for PVD. Very few chemical reactions are involved in PVD. Little wafer damage in PVD. Limitations are line of sight. This is one of the limitations. Shadowing occurs in the PVD. Shadowing means it can cover the straight one, this one recess, but when it is at some angle, it cannot completely cover the recess. So this is called line of sight and shadowing. Thickness, uniformity, difficult to evaporate materials with low vapor pressures. These are the limitations of PVD. Here are some of the, this is how the uniform isotopic emission from a point source. If the emission is like this would be a uniform. But in this case, ideal cosine emission, this is called ideal cosine emission. It's a different kind of deposition. And then this is a non-ideal, more anisotropic emission from a smaller planar surface source. So this is more anisotropic. This is less than that, and this is the ideal. This is a uniform isotropic emission from a point source. This is for different elements. You can see some of the parameters here. And in this slide, you can see if the deposition is uniform or not, and sticking coefficient SC, you can find F reacted over F incident. So this is how you can find the sticking coefficient SC. This is sputtering. This is for sputtering. These are the steps involved in sputtering. This is how sputtering occurs on the surface. And here are some of the constants you can see here. The comments also are given. You guys can see how these metals are oxides or nitrides and polysilicon, how these material nitrides, how these materials are being deposited on the surface, and then the constants involved for those materials. So with this, we end this lecture of thin film. Mostly we have studied the PVD and CVD system. Okay, so PVD and CVD are two versatile techniques used for the deposition of thin film. And thin film is basically a film from tens of nanometer to 100 nanometers. Or sometimes this is even less than 10 nanometers. It may be a few nanometers as well. And in case of graphene, it goes, even less than nanometer, within that range. So it varies according to some paper report, even 100 nanometer thin film, some paper report at even 10 nanometer thin film, but ultra thin film is below 10 nanometers. So this is how the thin film is being categorized, and the major techniques involved are CVD and PVD. With this, we end today's lecture. Assalamu alaikum and Allah Hafiz. And I can collect the questions from WhatsApp and from chat room. Thank you very much. Assalamu alaikum.